All right, so the third type of special discrete probability distribution we want to consider is the geometric distribution, okay? So the geometric distribution is a count of the number of x-independent Bernoulli trials required to obtain the first success, okay? With a constant probability of success for each trial. So in here, compared to the binomial distribution, we have the number of trials to be fixed or predetermined, and the number of success to be random. Okay, for binomial distribution, we have the number of success to be fixed or predetermined, and the number of trials to be random. But the geometric distribution is the opposite. We have the number of trials to be fixed or predetermined, and the number of success to be random instead. Okay. So where can we apply this? A geometric random variable can be found in situations like the number of pregnancies required until the first boy child is born, the number of oil wells needed to be drilled until the first successful oil well is hit, the number of shots fired until the first target was hit, etc. Okay, so this is basically showing us that the geometric distribution is a count of the number of independent Bernoulli trials required to obtain our first success. All right. Now, in the case where we are interested in the number of x-independent Bernoulli trials required to obtain the kth success, then that will give us a different distribution known as the negative binomial distribution. Okay. All right, so let's take a look at the formal definition for geometric distribution. Let the random variable x denote the number of trials until the first success occur in a series of independent Bernoulli trials with a constant probability p of success, okay? Then x has the geometric distribution with parameter p and pmf as defined in equation 3.1, okay? So for here, we have the probability of success to be p, 1 minus p is the probability of failure, and we have x to be the number of trials until the first success. Okay, all right. Now let's take a look at this framework. Sometimes the random variable of interest is the number of failures before the first success. Okay, so if you have to denote the random variable by y, then you can define the PMF of this random variable as shown in equation 3.2. So here we are looking at the PMF of the number of failures. Okay, the number of failures before our first success. So we have y starting from 0, 1, 2, up to infinity. Okay, so this is the number of failures before p our first success. Okay, so let's take note of this remark 1.3 equation 3.2. Okay, all right, so now let's take a look at some properties of geometric distribution. if x has the geometric if x has the geometric distribution with parameter p, then the expectation of the random variable x is equal to 1 out of p, which is similar to the mean. Okay, this is the mean. And the variance of the random variable is equal to 1 minus p divided by p squared, which is similar to q. If you have to replace 1 minus p by q, if you have to replace 1 minus p by q, then we'll have q divided by p squared. Okay, then we can also define the moment generation function in this form. Okay. All right, so before we take some example, let's take a look at some theorems. So the first theorem, let x have the geometric distribution with P and F defined here. Okay, we can also define this form, x running from 1 to infinity, where q is equal to 1 minus p. Then the probability that x is greater than a particular value of x can be written in this form, 1 minus p raised to the power x or q raised to the power x. Okay, so there's a proof to this theorem. Let's take a look at the proof. The probability that x is greater than a particular value of x can be written in this form, okay? Because we are going to discrete case. If x is greater than a particular value of x, then the next value will be x plus 1, and the subsequent one will be x plus 2, x plus 3 in that order, okay? So using the definition for let me take a look at this. Using the definition for the geometric distribution here, if I'm to replace x by x plus 1, then I'm going to obtain this, okay? If I'm to replace x by x plus 2, then I'll obtain that. If I'm to replace x by x plus 3, I'll obtain that in that order, okay? So once you factor out p and q raised to the power x out from this side, you're going to obtain this, okay? And you can say that this is similar to the sum of infinite geometric series, with the first term to be 1 and then common or constant ratio to be less than 1, okay? So we can basically rewrite this in this form, okay? So if I'm to replace x by q, then I can rewrite this as 1 divided by 1 minus q, okay, which is similar to what I have here, okay? Okay, so now we know that 1 minus q is similar to p, okay? So once we multiply through, we obtain this, and this will end the proof, okay? Very quite simple. Let's take a look at the second theorem, lack of memory property. If x has the geometric distribution, then the probability that x is greater than n plus n, given that x is greater than n, is equal to probability that x is greater than n for all positive integers n and n, okay? So what does the lack of memory property basically implies? Let's consider an experiment of rolling a fair die, okay? Now, suppose a 5 occurred 3 times in 20 rows of a die, then the probability that a 5 will occur during the next x rows of the die does not depend on the number of times it has occurred in the 20 rows of the die, okay? This basically means that the count of the number of trials until the next success can be started at any trial without changing the probability distribution of the random graph, okay? So that's basically the analogy behind the lack of memory property for the geometric distribution, okay? All right, so there's a proof to this theorem. Let's take a look at the proof. Probability that x is greater than n plus n, given that x is greater than m, is equal to that, okay? And we know this based on our knowledge on um, conditional probability, okay? So we can rewrite this in this form, okay? The intersection for these two, probability that x is greater than n plus n, and x being greater than n can be written in this form, okay? Because this one is embedded in this, okay? So the intersection will be in this form. So using theorem 1.31, we can rewrite this in this form, okay? So the numerator can be written in this form, and the denominator can be written in this form, and we can work this one out to obtain that, which is similar to that, okay? All right, so now let's take a look at an example. A large consignment of items contains 20% that are defective. Items are drawn into a defective item is found. We want to find the probability that 4 draws are required until a defective item is found. And secondly, less than 3 draws are required until a defective item is found, okay? All right, so now let's take a look at the solution. Let X denote the number of items drawn until a defective item is found. Then X has the geometric distribution with parameter P, which is equal to 0.2, so there's a probability that the defective item is found. So we can define our PMF in this form, okay? So we want to find the probability that 4 draws are required until a defective item is found, okay? And we know, and we quickly take a look at it again. So, okay, so we are looking at the probability that 4 draws are required until a defective item is found, okay? So using this formula here, can rewrite this in this one, okay? Which is equal to that, which will give us that, okay? Very quite simple. And second, we want to find probability that less than 3 draws are required until the defective item is found. And this is similar to that, okay? If it is less than 3, then we're looking at probability that x is less than or equal to 2. And we can also rewrite this in this form, okay? So when x is 1, we obtain that, and when x is 2, we obtain that, okay? So if you use the calculator to compute this, you obtain that, which is very quite simple, okay? All right, so now let's take a look at the alternative method for this example. Let y denote the number of non-defective items drawn until a defective item is found. So now we are using the second definition for the geometric distribution. Okay, so here we are now looking at the number of failures before we obtain our first success, okay? So then y has the geometric distribution with parameter q, which is equal to 1 minus p, which will be 0.8, okay? So then we can define our PMF in this form, okay? All right, so now I want to look at the probability that 4 draws are required until the defective item is found. So it means that we're supposed to observe 3 failures before we will look at the first success. Okay, so we have y to be equal to 3. So we can write this in this form. So we have to observe 3 failures or 3 non-defective items before we observe the fourth one to be the defective item. Okay, so the countdown will start from 0, 1, 2, 3. Okay, we are going to observe three followers or three indicator items, and then the fourth item will be our first success. Okay, so once you try to compute this, you obtain this, which is similar to the result we had under the first case. Okay, then secondly, we want to find probability that less than three draws are required when three defective items found. So this is equal to probability that one draw is required, plus probability that two draws are required. Okay, so basically we're looking at probability that at most two draws are required. Okay, so that's what we have here. So for one draw is required, we are going to observe a zero failure before we obtain our first success. And for two draws required, we are supposed to observe one failure or one defective item before we observe the success or defective item. Okay, so once you try to compute this, you obtain this, which is also similar to the result we had under the first case. Okay, so this is going to be a trial question. I'll leave the solution in the description of this video so you can check it out. Please, if you find value in today's video, don't forget to subscribe if you have not. And for your notice, there are no charges anytime you subscribe. It is free of charge, so don't be scared to subscribe if you have not. And thank you for watching.